Hello, space enthusiasts, and welcome to today's discussion on how to keep humans alive and well on the Red Planet. I'm fortunate to be joined today by Barry Finger, the Chief Engineer and Director of Life Support Systems at the Paragon Space Development Corporation. How are you doing today, Barry?
Hey, I'm doing pretty good, Ryan.
So yeah, I'm Ryan MacDonald. I'm a theoretical astrophysicist working on a PhD in astronomy at the University of Cambridge, where my research focuses on understanding the atmospheres of planets orbiting other stars. I'm also, of course, one of 100 people around the world who are currently involved in the astronaut selection process being conducted by Mars One. So firstly, to provide a little bit of background for those of you who don't know, Mars One is a not-for-profit organisation currently working towards the ambition of establishing a permanent human outpost on Mars in the year 2027. Mars One is a project management company whose principal activities revolve around selecting and training the crews of astronauts and, of course, raising the financial resources to realise one of the most exciting endeavours of this century. Now, since Mars One aren't themselves an aerospace company, what they do is they issue contracts to existing aerospace companies around the world with decades of experience in order to study, design, and indeed eventually construct each mission component. Paragon is one of these companies who have been studying the environmental control and life support systems, also known as ECLSS, which would be suitable to sustain a human presence on Mars. So Barry, could you tell us a little bit of background about Paragon and how you came to be involved with Mars One?
Sure. So Paragon's been around for almost 22 years. I think we're in our 22nd year now. We do life support and thermal control in extreme environments. That's what we like to say. We develop products and systems that people and vehicles can use to operate in those environments. And the company started out as a small company. 3 people basically didn't go to college and used their college loans to get the company started all those years ago. And then someone went to college and finished. But they got the company off the ground and going. They worked a lot in bioregenerative life support systems back in the day when they started. They flew a number of payloads to the Mir space station and then to ISS, some bioregenerative payloads again, small biospheres. And then the company progressed through. We started working with companies like Lockheed Martin, doing a lot of the early conceptual design of all the different, NASA's had so many vehicles through the years, OSP, CTV, CRV, and Paragon did a lot of work with companies like Lockheed Martin, helping to do the conceptual design of those systems required to keep them alive in those vehicles. And anyway, trying to keep it short, that work progressed into starting to build and design and manufacture hardware for the vehicles. And so that's where we've gotten to now. We now still do the front-end conceptual design work. We're also building flight hardware for vehicles like Orion, for the Boeing CST-100 commercial spacecraft. We're doing other kind of wild, crazy things like taking wannabe astronauts to the edge of space in balloons and having them parachute back down in a spacesuit. We've done things like that. So it's a wide range of things that we do, but it all focuses on life support and thermal control.
Well, that's absolutely fascinating. And of course, so where Mars One kind of stepped into this is back, I believe it was in 2013, Mars One began the process of commissioning conceptual design studies, and they selected Paragon in order to conduct the initial assessment of the life support that Mars One would intend to use. And this initial assessment was then released to the public in June of 2015. And following that release, I've received some absolutely great questions concerning the technologies involved and the next steps ahead in the study of what arguably I would say is the most critical component to any human mission to Mars. So let's dive straight into it then. So I was wondering if you could briefly elaborate on how your initial assessment fits into the wider picture of designing, developing, and eventually building a physical piece of space-rated hardware.
Okay, well, it's a good opening question. Some of it's going to be dry and boring. I'll probably try to keep it short. But you got to realize what Mars One is undertaking is what we call a system of systems. They're not just building a launch vehicle, not just building a rover or a habitat, but it's everything. So we're one important piece of the pie. And like I think you said, I do believe it's one of the most important because at the end of the day, when you look at all the systems that have to run and operate long term to go to the Mars environment and operate there, we've got a lot of experience with things like comm systems and power and propulsion. We don't have a lot of experience with long-term life support, so I do think it is one of the key systems. But having said that, your listeners need to remember that it's just one piece of the pie. So for us, we were glad to get going with Mars One. Like you said, about 2013 when we got going, and and we start with a conceptual design. And what Mars One is going to do is take our work, and then they start to break down or decompose their entire program into bite-sized pieces, I'll call it. And they have to develop these conceptual solutions for each element of the program. And all of that has to get assembled together into a comprehensive program that's shown to close. And that's what they're doing right now. As time is marching through, they're getting more and more of that done. And then the way it works is folks should realize it's not like you just come up with a conceptual design and then you start manufacturing it. It doesn't work that way. I wish it did. On the creative side, you can get going. You can have a lot of good ideas. You can brainstorm at the beginning. That is good. That's a good opportunity at the front end to do it. But what happens is it begins to be a very rigorous process to kind of steadily march through that development process. So we're at the very much what we call the front end of a program like this to get going. And the concept, so in brief, I say the concept will gel together. They'll have to show that it closes with the people that are doing the funding or financing for them. And our job is on the technical side, along with all the other technical folks, to show we got technical solutions that will close. And then they start to just really lay down, establish what we call requirements, the things, the shall statements. It shall be for this many people. It shall weigh no more than this. And they develop those requirements for all of the elements that comprise those system of systems. They get flown down, and we start going through design cycles. And the first one is called the system design cycle, and that's where you, at the top level, you show conceptually with the allocations of requirements. And another big thing in systems like this is probably, I don't know if this is boring the type of people that listen to you, but mass, power, and volume, and even dollars. Those are what Mars One. They're going to dole those out to all the different systems that make up the vehicle. And then they in turn dole them down to the subsystems like us. ECLSS is really a subsystem of the habitation system. And then our job is to show if we have a design that'll close within the mass, power, volume, and the cost. And that progresses through. So we show that closes. Now what happens in that process, so say you get to that first system design level, there's going to be breaks. There's going to be things that, hey, we just can't do it for that much mass, or the power people are going to say, we can't make that much power unless you give us more mass for more solar arrays, for example. Well, Mars One, like most program managers, they'll be smart. They'll have kept some reserve. And maybe the ECLSS will come back and say, hey, we can do it for less mass. So they'll steal mass from us to give to somebody else. And those types of processes have to go on, those handshakes and back and forth. And essentially what you end up doing is 3 levels of development: a system design phase, then a preliminary design phase, where again, now all the way down to the component level, you have a technical solution that you can show closes or is broken. And you get to the end of the preliminary design phase, and if something's broken, you go have that negotiation again. And you keep working till you've got something that closes. And then finally, you get to what we call the critical design phase. And that's where you're down to generating the drawings, getting down to the ounce, how much everything weighs, how much power it's going to take, who's going to manufacture every last piece part. And you end at that phase with the blueprints to go build your systems and components down to the component level. And then you pass on, you start to go to manufacturing and then testing. So it's a very well-established process. This is how aircraft are built. This is how major large ships are built. It's even how skyscrapers are built. They follow a very similar process. So it sounds like a lot, and it is a lot of work, but it's something that's been done routinely in the aerospace community.
Yeah, I think the key thing that you mentioned there is really the iterative nature of it. How you go through a number of designs, of course, refining things over time. And then it's not just obviously that you build the life support system. You have to understand what's happening with the other systems so that you know what kind of requirements you have to work with. So it's a very interlinked web of development, effectively.
That's right, right. And you've got to have that. You got to have those interactions. One of the where things can go wrong in systems, we call it stovepiping. If I'm only developing my ECLSS and I'm not paying attention to what other people are doing, invariably when you get down to that end, when you have to make everything reconcile, you can be too far out of bed. So it's very, you have those it's just very important to have those communications back and forth across all the subsystems. And ECLSS is one of those that just touches everything. Power systems, communication, data. You have to tap into almost every vehicle subsystem when you're doing the ECLSS.
Yeah, I mean, I can give one really obvious example for listeners. For instance, of course, we know that dust storms are a very frequent occurrence on Mars. And during a dust storm, if you're using principally solar power in order to generate your electricity, then you have to make sure the life support system is designed such that it can still function adequately during the duration of the dust storm.
Yeah, that's one of the issues we brought up. There's a trade there on the past. One of the trades we talked about on the power system. You can have bigger batteries and to get through those dust storms longer and keep running your systems maybe. Or you maybe it's a better trade to go for bigger storage buffers of the critical things for life, water and oxygen and argon and things like that.
So speaking about life, the key component that I really noticed within your initial ECLSS assessment is that it's what's called a physiochemical system, meaning that it relies on just principles of physics and chemistry and not biological systems in order to run the life support. So one question that I've received is about how complicated a process it would be to tie in a bioregenerative life support system into the pre-existing physiochemical life support system once, for instance, the first crops to feed people would start to get grown on Mars?
Yeah, so that's a good question. I should tell you, I started out in bioregenerative life support. That's where my career started. I was a starry-eyed engineer, young engineer, working with a bunch of plant physiologists and horticulturalists, and there's a lot of work been done in that area. But first, to your question, I guess, how could you do it? I don't think it's overly complex, but probably what people have to remember is you're not going to just flip a switch and suddenly your bioregenerative system is on. It's going to come up gradually over time. You're going to phase the growth of the plants in, and then eventually you'll reach a point where you're moving it's a lot of water. You're moving a lot of water through the plants. That's the first thing you'll do, because plants actually transpire a lot of water. And that's one of the first things we'll do. That'll become part of the water purification step. Plants actually do a great job when the water comes in through the root zone, and there's what we call the rhizosphere there, and the bacteria and fungi. They do a great job actually purifying the water, taking out contaminants. And the plants do an even better job when they do transpiration. That water goes up through them and evaporates into the atmosphere. But so it'll be a gradual process, and what you'll probably see is you'll start with growing a few plants. You'll start to get some edibles like salad type crops and things like that. That'll probably expand for a while, and then you'll start to see that water really being produced to them, and so it'll stepwise through that. And there's lots of folks and researchers and NASA and NASDA, the Russians as well. There's a lot of work been done over the years, going all the way back to the late 1980s, where a lot of work's been done to develop the models of how you would phase these in over time and do that gracefully. So I see it's all doable. What I'd say, one other point I wanted to make on that is you need buffers. You need one thing in these engineered systems. We don't like transients. We don't like things that happen really fast. And so we need adequate buffers of water, of gases for plants, CO2, and oxygen that's being produced. So you've got to have the ability to have buffers so that you can. That's where the humans come in, kind of do some fine tuning and regulation, because we're essentially creating an artificial ecosystem. So invariably, if you just think about the Earth's life cycle, there's sources and sinks of carbon. There's sources and sinks of oxygen. And so we have to engineer that into these very compact solutions, if you will, for bioregenerative life support.
Yeah, and in the language of physics, of course, it's all with our dynamical systems about finding the steady state. And so it makes absolute sense that you have a basic life support system that runs just on physics and chemistry to establish the key needs, and then gradually phasing in all of the plant-based life so that you can gradually tap into the benefits whilst also not risking at all destabilizing the environment. So yeah, I definitely think that's the right way to approach it.
Okay, good. I'm glad you agree.
So we've had a few questions as well about EVAs, or extravehicular activity, and in particular to do with suits that you would require to actually go outside on the surface of Mars protected. Because in addition to the initial ECLSS study that Mars One commissioned with Paragon, There was also one on possible designs for suits for this purpose. So I was wondering if you could tell us a little bit about the current status of your suit design study.
Yeah. Unfortunately, I won't be able to tell you too much because of U.S. export control laws.
Ah,
Uh,
yes, ITAR.
now, it turns out the suits are still covered under export control, and it's a really funny thing. We can laugh about it, but apparently a bad guy could wear a spacesuit and fly a missile back to the ground as we were thinking, or something along those lines, wearing the spacesuit. We were able to release the ECLSS habitat study fully because that was determined by from the U.S. side that there was no ITAR or expert compliance issues we had to worry about. The suit study we actually delivered, I think, back in October of last year to Mars One, so they have that. We've met with them, we've fully debriefed them. They have that. No, that might be enough for them and what they're doing to move forward. Again, that's an example of another one of the studies that are done. I'm sure they want to release that to the public, but it'll be, is it worth it to them? Because they have to do a little bit more work to essentially sanitize it so it can be available for public release. I guess I just tell you in general, the suits do present a challenge because you have to make a suit that just is robust and reliable and can be completely maintained in the field. And so that's very different if you followed anything like NASA or the Russians have done, where the suits have limited life. They come back to the ground on the U.S. side for refurbishment. The Russians use them several times and then actually just throw them away. So that's an area, but there's been tremendous, again, work done in that area over the last 30 years. And there's a whole industry still, even though space is small, human space is small, there's an incredible number of people and organizations that have been working on these problems for years and decades, and they're just waiting to essentially exercise what they've learned. So we're saying as confident. We've provided mass, power, and volume numbers to go put those systems on the surface, and we'll see where it goes.
Great. There was one last question I had about suits, though, which was, of course, unlike our home planet, the Earth, Mars is continually bombarded by radiation, principally from the sun and elsewhere in the galaxy. So do you know of any ideas that are currently floating about in order to provide radiation protection within the suits? And I mean, one that I've heard is about boron nitride nanotube fibers. So any ideas along those lines?
Well, I'm not a textiles expert or radiation expert. I can tell you that right now. I do know it's all about shielding. That's from what I've seen. And if you can get, we like water. We like things with hydrogen. So if you've got those types of materials to choose from, and maybe that's what the material you mentioned is potentially offering. I think those are the ways we're going to go in the near term. When you think about radiation, this has been brought up a lot, not just on Mars One, but other programs we've worked. And there's a camp out that says the radiation is going to kill you, you're done, and you're going to be cooked. And I think it's going to be a proper management. There's time management about how much you're in those environments. So if, for example, you're in a rover, and maybe we may make sure the rover, when you're going from one place to the other outside, it provides a lot of that shielding. It's a lot easier to do that probably on a vehicle like that.
Okay.
And then so time management, and then ultimately keeping close track on the total exposure times that people are exposed to on the surface. But if you can get to an actual material construction that provides significant shielding, we'd have to get some more folks involved to really dig deeper and see if that's what I'd say is one example of. I don't think you should make that be the reason you don't go to Mars now. We might have to really limit your time. It might be just like in society, the old timers don't get to do what all the young people do. So maybe the old timers aren't going out as much and doing the external maintenance, and they're working more on the interior system. So maybe it's like you'll have a lifetime that you can do this many EVAs and then you're done for those first generations. I guess we'll have to see on some of that stuff, but yeah.
Yeah, I mean, it's a point to emphasize that radiation really isn't a showstopper for Mars, because the habitat itself is designed that it would be partially submerged to block out a large part of the radiation. But of course, limit your time outside. Don't go outside for more than, say, 7 hours a week or so. And then even with minimal shielding, it should be fine.
Right, yeah. That planet does a pretty good shielding from one direction, right?
Yeah, definitely. So we mentioned earlier about storage tanks or buffers for the key things you need for life support, such as water, for instance. So if you want to store a large amount of water to be able to last through a dust storm, for instance, if you want a tank that can store up to 1,500 litres, of course, they'll require a very large volume. So one question that I've received is, where will you actually put these storage tanks? Because if you put them externally to the habitat and then pipe them inwards, you'd have to have some kind of thermal insulation and heat the lines because, of course, it's very cold on Mars, average temperature around -50 or so Celsius. So where do you think the tanks should go?
Well, so if you read our review, and I'm sure you read our report in detail, and your viewers have too, you can kind of see we kind of were figuring that out a little bit as we went. We realized we wanted buffers. We talked about that earlier, these adequate sized buffers. And it's maybe you could have tanks that are deployed. We see soft good tanks as being essential, essentially, to or bladder type tanks. And they could be deployed from the ECLSS lander itself. The problem with that is that you're going to have a mass hit on the lander, and we're already pretty heavy now as it is. So when we started digging around a little more and looking at it, their habitat, the habitat where the crew are, is a deployable habitat. They state that, and Mars One wants to run that way. We've actually done work with a company called Thin Red Line in the past, where we integrate things like tanks and structures into inflatable habitats or deployable habitats, and so maybe they'll be external to the habitats themselves, and then what you're saying, we have to worry about pressure and temperature and radiation exposure and dust exposure and all those things. But it might get a lot easier if we're just integrating, basically think of a bladder tank inside of an inflatable habitat. And we're not the first ones to think about that. Other people have talked about that and looked at it. But it seems to be, what we know is that the thing that's going to keep you alive, if you're there, is having these stores of oxygen and water and pressure and gas. They're going to be essential to your long-term survival. You got to pay that price to be able to have the room for those storage buffers. And so you're going to have what we're telling Mars One is you've got to find a way to make these part of your system.
And I mean, at first glance, it sounds like an excellent idea to actually, for instance, have the water tanks built into part of the inflatable habitat. Because, of course, water, H2O, contains a lot of hydrogen. And since most of the radiation coming from the sun is just protons or hydrogen nuclei, they interact most strongly. The interaction cross-section is greater. So it would actually act as an extra layer of radiation shielding to integrate that as well. So, yeah, I certainly think there's potential to explore that.
Yeah. Okay. Good. See, we need you on the team.
Yeah, definitely. But there is one problem, of course, from having the habitat underground, namely about the issue of natural light. Because, of course, you can survive, you can have your water and oxygen, be perfectly happy. But with regards to being healthy, some people have asked me if there's any way to get natural light to enter the habitat for vitamin D production.
It's a good question. Again, I'll say this is not one of my areas of expertise, but I know back in the day when I was doing environmental life support, there was a fair amount of work that people did on what they call light pipes. And that's you have an external collector, and it could be a reflector or a refractor, and they're collecting the light waves and then piping them in to the plant growth chambers, because that's one of the challenges with plants. It takes a lot of energy if you're going to use artificial light to grow them. So I think there's been a lot of good work there. I mean, you can buy them for your house now. You see the light pipes that do natural light inside a house. I don't know if you have those over there where you are, but they're kind of neat. A couple of just practical things to keep in mind. The light level at Mars is already pretty low. And so if you think about it, if you want to have Mars level surface light, then the collector that collects the light has to be as big as the area you want to illuminate. Or if you want more light, it's got to be, say twice. If you want twice as much light, it's got to be twice as big. And then you have transmission losses in a system like that. But I do think that's possible, and it'll be interesting when you do the trades if it'll be essential. If to get going initially for those first few missions, if you have to have it, or you can get by with taking the power hit. But the other thing I know is people like that natural light for psychological reasons and just mental well-being. So you might want to invest in that.
Yeah, definitely. But if we're thinking about the long-term future, then obviously it's absolutely vital to have a life support system that can last for a long amount of times. And if it does break, it obviously helps if you have spare parts available to be able to fix it locally on Mars, instead of just having to rely on, say, on a single life support module, because there'll be two of them initially. So I noticed in your original assessment that you mentioned briefly about compatibility with 3D printing for replacement parts for the life support. So I was wondering if you could elaborate on the level of technological readiness on this regard?
Okay. Well, so again, I like to tell you what I'm an expert, not expert. I'm not an expert there. Our company actually does. We're doing work in additive manufacturing. Again, if you go out and look at what's going on in the world now, it's incredible. I think we're on a big cusp of a sea change in how manufacturing is done. And I'm not talking about the home 3D printers like my children have. I'm talking about manufacturing. It's just incredible what's being done now. So talking from what I've been exposed to as a chief engineer and what our company does, we build parts now routinely for systems that we're putting out there. The Stratix program, where we took a guy to the stratosphere and parachuted back, there were 3D printed parts in that system that were operational and used over and over again in the suit system itself too, that was used in that. We're finding that it saves time, it saves money, you can do faster design cycles. So having said all that, when Mars One is ready to go, if they stick to their timeline right now, I just my personal opinion, but I think there'll be some type of additive manufacturing or 3D printing that's on board. You're not going to be building circuit boards or anything like that, but the basics of life, plumbing connectors, switches, housings, filter elements, maybe wear parts that are on the suits, wear parts on the rovers. I can just see lots of things like that going on. And given the advancement that I'm seeing with the technology today, especially in Mars, you're in a gravity environment. There's 3D printers now they're working on at ISS that are starting to be developed now, and they've shown some good success there in a microgravity environment. I got to believe it's only easier if you're going back and designing one for a gravity environment. So I think that's promising. And last thing I just say on that is we don't rely on that though in the solution that we put together. We just say we think that could, if when they do those trades and mass is still a little high, that might be where Mars One puts some of its investment dollars to make sure that technology is ready.
Yeah, I mean, of course, technology readiness is really the key with this, and it's part of doing these design studies to figure out what is ready, what needs more development, and then hence plot the best course forward in moving forward with the program. So I've received a few questions now about some of the individual subsystems that make up the ECLSS. So let's start with water just to begin with. So I had, well, one particular doctor asked me about whether the water purification system will be capable of eliminating hormones, particularly estrogens.
So a good question. So I know, and again, in terrestrial situations now, that's becoming a problem, and they're showing up in the water. And what I'd say is, again, let me think about it. I think one of the ways I know that you could probably handle that right away is you make sure you're using distillation processes, and that's one of the things one of our major steps is a distillation process that we propose for the baseline technology we selected for urine and feces, which I believe would be your two primary transmission pathways of getting those into the water system. So if you do that right there, you just have a physical barrier that prevents them. And that's maybe a difference than the water cycle here on Earth, where we do wastewater treatment. And if you think about wastewater treatment on Earth, you heard that you don't usually pay the energy cost to phase change the water because it costs energy to do that. So the water tends to flow through, staying in a liquid form all the way through, and contaminants are removed by different processes. And that's where those estrogens may be slipping through. But if you use a distillation process like we propose, then I think you're going to find that's a pretty hard barrier to those passing back through to the potable water.
Oh, yeah, I hadn't thought about that. No, that's... Yes, yeah, I can certainly see that working. It is really interesting, actually, to contrast how there is a different way to keep people alive using these artificial systems than the natural systems that we're used to here on the Earth.
Yeah.
So, another question I had, though, about another thing you might want to consider removing from the water supply is, have you considered removing deuterium and tritium as part of the treatment process?
Those are isotopes of hydrogen, is that right? So okay, and again, I'll have to look at that. Well, first thing I'd say is, what I hear a lot, and I've been actually done water processing for a big chunk of my career. One of the questions I always would ask is, how clean is clean enough? So, and how bad is it? And so first thing I want to know is really, what are those contaminant levels? And so I think that's one of the things I'd say we really want to get a handle on. And I think that was actually in our study, we talked that was one of the risks we identified, to make sure we know early what's actually in the water, so we know what has to be cleaned up. So I'm not really up on those particular ones. I don't know if you could take advantage of maybe again. Well, I bet it's going to behave just like pretty much like regular water, but maybe there's physical differences in boiling temperatures or freezing temperatures, and maybe you could do phase change like that. But the first step to do is figure out what's there and is it dangerous, and then so maybe you check in with me again on that, and I'll do a little homework on that to see and get you how we can solve it from the get-go.
Yeah, well, my understanding is that deuterium isn't especially harmful because, I mean, usually about 1 part in 10,000 of ocean water is deuterium. But tritium can get slightly radioactive, so that might be where some of the concerns are coming in there.
Yeah.
But with regards to cleaning things up, though, I had one message from actually a sustainability expert who's fascinated by waste management solutions. So they were wondering if you could talk briefly about what types of closed-loop waste management systems you considered as part of your architecture.
So what, when you say waste management, are you talking about the toilet, or are you talking about the systems that recycle the water or the oxygen, or?
Well, I imagine principally the what emerges from the posterior.
Okay, so that's a interesting problem. It's a fun problem, something we talk about, laugh about all the time. In fact, one of our researchers that does a lot of our water processing systems, she's now Dr. Poop, is what we call her. So, but what we baselined, and I'll say just so again, so you people don't think that this is a system that's going to fly. But for this conceptual design, we baselined what we call a wet waste management system. So things like urine and feces and wet trash go into a system that we use this phase change process. We really like that because it's just a lot of the contaminants. If you think of volatile and involatile, non-volatile contaminants, a lot of them stay behind. They want to stay in a solid form or in a liquid form. So if you just phase change the water, right there you get a purification step because it's only what will go volatile will move with the water. So that helps right there. And then we got to have some technology that's ours that we developed in this. And we've been developing a technology, the membrane processing technology, that uses a particular material that's very good at basically just passing water. It'll pass it in liquid form or the vapor form. And then just a few other contaminants will get through. So we like the idea of what we call wet waste management system, where it's I'll call it brute force, phase changing that water, using some novel materials that have long lives and they're used in industry now for other applications, not water processing. They soon will be. We can talk about that later. Yeah, so that's for feces what we see. Now, what's going to happen over time? It's not going to be a fun job, but at some point you're going to have a collection of sludge that needs to be removed from the processor, and you guys on the surface are going to need something to do. So someone's going to get that job to go in and clean out the potty. And the truth is, it's funny. So we laugh about those things, but not in the first few years of the habitat, or maybe not even in the first decade. But I tell people all the time that pile of organics and inorganics that you're taking out is going to be a gold mine, because as you start to do fully regenerative and closed loop systems, there's all the stuff of life concentrated in that waste. And you'll probably stabilize it. Just you'll pull it out, you'll stabilize it, you'll probably expose it to vacuum, essentially freeze dry it, and then you will accumulate that. And again, we talk in the space systems, you got to deal with it. It's more shielding in the short term. It's more shielding. You for planetary protection reasons, you're not going to just put it outside the habitat. You're going to put it in some type of container, but it just becomes another layer of shielding for your habitat.
Well, I'm sure many of our viewers will remember, of course, that during The Martian, when Mark Watney got stranded, one of the first things he did was go to that organic gold mine in order to reprocess them all for agricultural purposes.
That's right. Yeah.
So now, before we wrap up, we've got a few questions about some of the hard requirements of the ECLSS module itself. So firstly, I was wondering if you'd comment a little on the current volume estimates of each ECLSS subsystem.
Well, I don't have the numbers in front of me. I could get them out if you want me to. We do have those in the report. You can see, if you want to go below to the subsystem level and all that, our model has that data, but we chose to roll it up there into that little bit higher level, so you see it for the water system and the air. And if you want me to, I can dig those numbers up and we can talk about it if you have specific questions on them.
No, probably the main discussion was of all the subsystems, what would you say dominated, for instance, the mass and volume requirements?
Well, for volume, it was tankage. Tankage really adds up, and so I guess what I'd say there is those numbers are so high on the tankage that you're not going to enclose them in a lander that's probably practical for the initial mission. The volume is just too great. So that drives you to what we talked about earlier, these deployable tanks or soft good tanks. And so maybe that's just one thing to take away. The mass and power of, you didn't ask about power, but the ISRU system, that's pretty high there too. And and so just saying that it's a reality, we think those systems, if you think about what we're proposing for the baseline life support, a lot of the kind of what I'll call traditional closed loop systems, they've got a lot of good experience in space now. A lot of what we pull from initially is flown. And so there's good history there. When you think about the ISRU systems, although the physical processes that are used are nothing exotic or new, like our baseline on the ISRU was basically using a cryogenic air system, or cryogenic gas system, I'll say, because there's not air on Mars, where we freeze out, we basically fractionate the atmosphere. And those systems we're actually working to scale down from the industrialized processes that are very mature and used all over the world now to produce specialty gases. And so there, we're probably just being a little conservative, recognizing that a lot of times when you go to scale down a process, it's as hard as it is scaling up sometimes. So I don't know if that scratched the itch there.
Yeah, no, great. And it leads naturally into the next question about potential areas for scaling down. So one of the key parameters of your initial module design that I particularly noticed was that the initial mass estimate of the module was around 7.5 metric tons. Now, of course, that is a very large amount to try and land on Mars in one go. For comparison, Curiosity was around 1 metric ton. So, but you also mentioned in your report that this was an unconstrained mass estimate. So if mass wasn't a worry, what would be the most kind of idealized system that could be produced? So I was wondering, yeah, sorry, do you want to say something?
No, I was going to say that one of our system engineers put that word in there because he's right. That is our unconstrained mass. But go ahead, you want to finish your question?
Yeah, so I was just wondering, so if, say, you were to put constraints on it, I was wondering if you had an estimate for a lower mass limit than the 7.5 tons that could be achieved with more efficient and necessarily more expensive solutions.
Okay, so good question. And your very first question that you started about how do you actually come up with a product, and we kind of talked through that development cycle. I'm going to start all the way back there. We're at that front end, and what I'd say right now is I hope I'm bigger than any other people fighting for mass or volume, so that I can win, and they don't take mine away. And so it's kind of a joke, but seriously, what I would say at this point, I would be hard pressed to get moved off the numbers that we have, because what I predict will happen is if you start optimizing now at the front end of the process, what you're going to get I think you'll get in a very bad position. And it's like what we talked about with this mission. There's some things, and I think we talked about it in the study. We have got to have electrical power. These people, you cannot live without electrical power. Then you've got to have pressurized volumes that don't leak. So those are two things that have nothing to do with the ECLSS, but they have to be there. Then the third thing is the stuff of life, the oxygen and the water and the pressure and gas that keeps that bubble around you, the pressurized gas. You've got to have those three things, and if on the life support side, and if you start trading away those or the mechanisms and machines or the processes for how you make those products at the front end, I just believe you're going to get into a very bad place right away. So I guess what I'm telling you is we're going to resist really hard as Mars One moves forward to move off those numbers. We propose things like, hey, because let's say this, do some things, spend some more money on your landers. Let's take it up a level. Mars One needs to do a trade study across. Do I put more money into developing a landing mass capability? Do I put more money, like you were talking about, into designing the ECLSS? Hey, we'd love you to send all kinds of money our way, and we can develop the most exotic life support system. It runs like a Ferrari, and it'll stay right at the top of its performance envelope until something goes wrong, and then it'll come apart. So what we're saying is, honestly, what I'm saying is, I think we'd push back and say, do a trade. Make sure you really want to put your money there in trying to perfect the ECLSS. I believe all the surface systems will benefit the most from being able to land more mass, or change your business model a little bit, do more launches. Maybe it's just two landers. Maybe, and I'll be honest, as we were doing this, and I don't think this made it into the report, but we talked this with Boss Lonsdorp, that maybe the ECLSS and the ISRU module are really end up being separate. People have to realize, again, you look at the concept art and what's there now. When you're at the front end of a program like this, your initial concepts hardly ever look like the final solution. So I'm kind of all over the place there, but I'm pushing back, saying don't cut my numbers right now. Let's look at system alternatives before you really make me go do that.
Yeah, no, so there was two main comments that I noticed there, and you seem to cover them quite adequately. So, I mean, initially, Mars One was estimating that roughly they'd be able to land about 2.5 metric tons. Now what they're going through with their next round of design studies is that they're actually going to be commissioning a study with Lockheed Martin, as you say, to look at the current landing system capabilities. Of course, every single system you have benefits if you can land more on Mars. But and also, as you mentioned, I suppose that if, for instance, say you find that the maximum you can land is 5 tons, for instance, then just split up part of the life support system, use different landers, as you mentioned, with in situ resource utilization in a separate module. So it's important to emphasize that just when you see a number like 7.5 tons, you don't need to land it all in one go. You can have more launches.
Right. You got to have flexibility in the process, and again, obviously, at some point, yeah, we can't land 10 landers that for break the ECLSS up into 10. But there's no reason at this point that it has to be one. 10, yes, that's too many, but there's some number in there that's right that we can at the program level. I'm sure they can make close.
And so, we're moving forward into the final questions now. So, of course, one of the key requirements in order to enable humans to live on Mars in the long term and to be as independent from Earth as possible is that you have to be able to use local resources from Mars itself. So one of the numbers that I noticed was that you estimate you require about 200 kilograms per day of Martian surface material, or regolith, to be fed into the ISRU module in order to extract water for the purposes of the people living on Mars. So I was wondering to what extent recycling efficiencies were factored into this and how much that number could potentially be reduced further.
Yeah. So I don't want to sound like a broken record, but we were actually pretty conservative. I think we only assumed 75% or 85% actual water recovery in the habitat. In reality, I think it'll be much higher than that. But that's what drove a lot of those numbers. And what I just tell you now is it's really the same thing. I am a broken record. Don't scrimp on that ISRU system because I can guarantee one thing is you will be living off the land if you're there for the long term. You will not be living in a habitat that's 100% closed and all you have is electrical power coming in. You're recycling the carbon and the nitrogen. Just life, the way that life works is you get byproducts and things that just aren't useful, or it's going to take a lot of work to turn them back into useful products. So you will have mass moving in and out of this system. And again, it's like I don't know a good analogy, but you don't want to scrimp there right now. And we talked about this because this is some people say, you got to get this down. They're picturing a little Sojourner rover trying to get that much soil or whatever. It's going to be tough to do. But I can't remember the numbers, but it was only like 8 cubic feet, something like that, of material we're talking about at typical Mars regolith density. So yes, it's going to be a push, but just and we're not going to have the systems you see on Earth for moving material and regolith around. We're not going to have the mining systems like there. But 8 cubic feet, you're getting that every day. Now I will tell you, we had some iterations with Boss on Mars One and Boss Lonsdorp. There are things like we had some pretty conservative assumptions how many times they were cycling the airlocks and going through. And we think there's some simple things that we're talking about operations, how much time you spend outside. The other thing is like, hey, if 2 people are going outside to the habitat state, they're going out together. So we're not cycling the airlock once for each one of them. So right there, we actually lose a fair amount of mass just cycling the airlock because you never get it all out. You don't perfectly pump that back into the habitat. So there is probably some conservatism there, but I'd like to challenge the RSU folks that'll be developing those systems to, I do want to throw them a little bit more money or a little bit more time, so that they can go work on that and get as robust a solution developed as possible.
So, and to wrap up then with our final question, looking at solutions and next steps, I was wondering if you could briefly comment on, so we talked about the kind of the overall architecture of a design process. So what would you say is the next immediate step moving forward with the ECLSS design?
Well, so with the ECLSS, one thing I'll just tell you, we could wait. We could wait now. We think Mars One has the information they need. And as they start to fill out all the rest of the systems, they got to get all this kind of data and get it all pulled together. Some will be easier than maybe the parts that we have. We could wait a little bit. If I do personally believe, try not to be biased here, but ECLSS is really important. So we identified, and I'm not going to remember all of them, but we had a whole list of risks and opportunities identified. I know one was like we talked about the water quality. We talked about a water demonstrations. I know that was one where they're going to, that early precursor mission, they want to do the lander. So getting some real data there on water quality would be important. Demonstrating some ability to process water, we think would be great. So there's a range of things like that. Getting going on a test bed, because again, one of the things we say about life support, if you in systems, a lot of times you can accelerate the testing cycle. You can go through high temperature cycles and high pressure cycles on structural systems. You can over vibrate them and shock them, and you can simulate a lifetime's worth of work. But in ECLSS systems, what'll get you are physiochemical, or biological or chemical processes that happen over time. And you can't necessarily speed them up, especially the biological ones. You get bacteria, fungi, mold, you get things growing where you don't expect them to. The other thing is the mechanical wear and tear. You'd be surprised at chemical deposition and biological biofilms, how much they have mucked up life support systems, machinery and equipment. It's really amazing. It's very simple. You think about it, the physical processes are understood why these things deposit out. Whenever we have a problem like this, we see them. A chemist goes, "Oh yeah, of course that's going to happen," and but it happens. So the point there is that getting these systems running and operating, they won't be the final flight systems. We do think that's something that Mars One could invest in, and it will pay off, because we have to build. ECLSS is about building these machines that operate for a long time and do so reliably. And that's the challenging part, because you have electromechanical components that have to work day in and day out, nonstop. So I guess I'd end with that. I'd say if they were going to do work on ECLSS, getting going on a mock-up of the habitat, starting to look at some of these processors in, and showing that you can build these machines that run and operate for extended times.
Great. So I'll say, that's been absolutely fascinating. I'm sure there's many people that are interested in learning more about environmental control and life support systems. So what I'll say is, if there's anyone watching who's interested in actually delving into the technical details of Paragon's initial assessment, you can readily find that on Mars One's website. You can just search on Google for Mars One ECLSS and you'll find it immediately. If you do have any further questions, of course, we'd love to hear them. You can send them into Paragon by tweeting at Paragon SDC, or if you have any questions about Mars One, you can contact me at Martian Colonist. And if you'd like further updates about Mars One, I also produce regular monthly updates over on YouTube at youtube.com/Martian Colonist. So from both of us here, bye for now.
All right, take care.